So where we were discussing about the conservation of momentum, right? So we wanted to have relationship between sigma and no, essentially we want sigma in terms of velocity. Sorry, we want sigma in terms of velocities, but sigma is not measurable, or this stress tensor is not measurable. What is measurable is strain rate tensor. Strain rate tensor is a measurable. It's a measurable one. Okay. And this strain rate tensor is then in terms of U, and then now our objective is to find out a relationship between sigma and epsilon, stress and strain rate. Okay, that is our objective. So to fulfill that objective, Stokes given a general relationship. Stokes gave a general relationship which is sigma ij is equals to negative PD plus lambda epsilon k k. This is a equation in a index form, okay, Einstein index notation form, plus 2 mu epsilon ij. So here it is called as a thermodynamic pressure. And this particular, so we know that this tensor have a trace of sigma ij, which is nothing but equals to negative of 3p. Now p, here p is a static pressure, not thermodynamic, static pressure. Okay, it is also called as the mechanical pressure. And there are two different things, mechanical pressure. Okay, also this trace of epsilon kk, is nothing but equals to del dot u. Okay. So using this, one can write the above equation as PD minus P is equals to lambda plus 2 by 3 mu del dot u. Okay. So now for some particular case, now for some particular case only,
Excuse me, sir.
yeah,
So where did you get PD minus P?
you substitute these values of sigma ij. Sigma ij is 3p and PD minus P, we are taking it out. And this, we are arranging this 2 by 3 mu sigma ij and these things. If you bring in, then you will get this particular form. So
Okay.
here ij is also taken as there will be some ij values when they will become I is equals to j value. So that 2 by 3 term will come into a picture. Okay.
Fine, sir. Fine.
Yeah. Delta ij is like a identity matrix. If this is a 3 by 3 system, then delta ij is a 3 by 3 identity matrix. This is called as Kronecker delta. So this, now we have again problem. Okay, so this particular part we are looking at in red. This is a gray area in that fluid mechanics. This is the highest assumption. So here lambda is one viscosity, mu is another viscosity, and generally we talk about this viscosity which is larger in magnitude compared to this viscosity. This viscosity lambda comes into picture when you have a compressible flow. Okay. So Stokes hypothesis comes into picture. He made some hypothesis which is called a Stokes hypothesis, which says that 3 lambda plus 2 mu is very small than 1. Okay. So the sum is very small than 1. So taking advantage of this, you know, we can then say that PD minus P, that difference is very small. So PD can be, it essentially allows us to say that thermodynamic pressure is nothing but equals to mechanical pressure and static pressure. So that dilemma, that goes in out, and then we can write this sigma ij simply again into a form which is P delta ij. Okay. Now this is only pressure on a plane, normal pressure, normal entity. This is a normal entity plus mu 2 epsilon ij 2 by 3 del dot u delta I. Okay, you can write like this, and these things are obtained from the measurements, and this type of equations should satisfy a certain constraint. These equations have been came from experiments, and this has to satisfy second law of thermodynamics. Thermodynamics has to be satisfied by this equation. Equations. So for constant mu and constant rho, and for incompressible flow, we can write this equation. For incompressible flow, and for constant rho and mu, we can write the equation rho du dt del u dt, del u del t, or you can write du dt also, but I want to keep it in a full form, plus u dot is equals to chi minus gradient of p, not rho, plus mu del square u. Okay. So if you see previous equation, it can be written like this, uh, and this things mu, and this will give you del square u, del u things will be coming into picture. Okay. Because del dot sigma is there. Okay, so del dot sigma, del dot of this will give you mu del square u, and mu only will be considered. Out of this del dot u for compressible, this will go out. This will become 0 for incompressible flow. So this term will not be there. This terms to mu, this thing will be there, and this is already del dot u. So del dot u, this is nothing but del dot of del dot u, yeah, or del of del dot u. So that is del square u. Okay. Okay. So this is called as the equation, governing equation for conservation of momentum. And this is a vector equation where u is a vector quantity, and it can be defined as, u can be defined as, in a component form, it is a u component, j v component, k w component, like this. So you can write a x momentum equation, or if you are in a Cartesian, so it is in a Cartesian coordinate, then x momentum equation will be, x momentum equation will be x momentum equation, this will become del u del t plus u. Now you can expand this, and it will be del u del x plus v del u del y plus w del u del z equals to, this chi remains same, and this del p del, so you chi can be chi x, and del p del x plus mu, this you can write as del square u del x square plus del square u del y square plus del square u del g square. Similarly, y momentum equation can be written as rho del v del t plus u del v del x plus v del v del y plus w del v del z is equals to chi y component del p del y plus mu del 2v del x2 plus del 2v del y2 plus del 2v del z2. Similarly, you can have a z momentum equation, rho Okay. Like this, you can, simplify that. Now, what is the
So,
physical significance of this? What is the physical significance of this? Yeah. Yes. Who was telling? Rejoy?
uh, so one doubt, sir.
Mm.
Sir,
Yeah.
you have written U del U, na, sir. U
Where?
dot del U. The first, the equation which
No,
you
no.
put in bracket.
There is no dot.
So it's U into del U, na, sir.
Hmm.
Sir, so
Okay.
when you have written x momentum, why have you changed everywhere U, V, and W, sir? Should it be U del U by del x plus U
Because
del?
because this U is nothing but IU JV KW. So if you write that in this particular form, then you can get like this. Okay, you write
Sir,
the difference
so it is
del.
actually a dot product.
Yeah,
Okay.
it is a dot product. It is a dot product. You can write here no dot only.
Okay,
Okay,
sir. Got it.
but dot has to be with vector quantity. And can I have but essentially it is a dot product. No need to have dot product with vectors only. It will be with scalar.
Okay, sir. Got it.
Okay.
Excuse me, sir.
Yeah.
Sir, everywhere epsilon is strain rate actually, right, sir?
Yeah. Strain rate. Yeah. Strain rate
Not
tensor.
strain.
Strain
Okay,
rate. It's not
okay,
strain. In
okay,
fluid mechanics, we have to talk about strain rate. That is the reason it will get is as a velocity gradient.
okay,
That
sir.
is the
Okay,
reason you are getting
fine.
velocity gradients here. Rate of change of volume. This del dot V is nothing but equals to this del dot V is nothing but is equals to rate of change of volume, you know, uh, per unit time. Rate of change of volume per unit time,
Yeah,
per unit volume. So it is
okay,
nothing but del dot U.
okay, sir.
So it's a strain rate. So here there is no cross product. Okay, in this there is no cross product. Tensor product is there. Tensor product is already gone. So that pressure is, I mean, that sigma was a tensor. So there, that product, tensor product is there. Okay, now comes to what is the physical significance of this. So what is the physical significance of this first terms? So what this first terms indicates? These are local terms, okay? And this is a convection term. This is your, gravity. This is your pressure, and this is your viscous term. Okay. So knowing the meaning of the terms, these terms gives you inertia. Okay. This is what gives you the inertia, which are essentially giving you shear stresses. And this is, the pressure. Now, this is, you can again say that this is the friction term. Okay. This is what happens locally, locally how the velocity is changing, how the JIT component or you can say in general, how the velocity is changing or how the momentum is changing with respect to time in this control volume. Okay. And this U dot gradient of U is showing you, suppose there is a velocity gradient happen in here, and there is a flow velocity moving. It's like coming and going. So as if you are standing here, you will observe, suppose you are standing here, you will observe that locally you may feel change in a momentum. Suddenly you will see some force, suddenly you will feel some, some change in the force here. Okay. So that whatever you are observing here, those kind of change in momentum, that is nothing but local change. But suddenly you may also see that there is a specific, something momentum is coming and then living, passing by you. It is like train coming fastly to you and immediately you feel the effect and it goes away. Okay. So this movement is happening, movement of this momentum is happening due to these velocities. So you have u velocity, v velocity, w velocity. So along this, the gradient of del u del x moving with this velocity. Okay. So that you feel the change, you know, especially if you are here, you see the some change. If you go here, you see the some change. If you move with that velocity u, you feel that change, this gradient del u del x. Similarly, in y direction, if you move with that velocity v, you will feel the change of u in y direction, del u del y. Okay. And pressure is what are the pressure you are feeling at inside that domain along that axis. And here, whatever you see, these are viscous terms. Okay, viscous terms, and here these are also like a viscous diffusion terms. Okay. So here in this case, we have seen that momentum is transferred through these velocities. Okay. Now here there is no bulk motion. You can say that convection is a bulk motion. So this is a bulk motion through which, through this bulk motion, the momentum is transferred from this location to this location or this location to this location. Okay. Because of that bulk motion. But here, without any bulk motion also, you may have the movement of, momentum transfer. So how it can be? So you know that we have, microscopically we have molecules, and these molecules, they transfer the momentum to nearby molecule. Okay. And this process is called a diffusion process. Momentum is getting diffused into another molecule, then they will transfer momentum to another molecule, nearby molecule. So similarly, the momentum is transferred from this A location to maybe a B location without any bulk motion, only through this chain of molecules. Okay. So this molecule passes on, this molecule passes on to that. Similarly, it will pass on to another molecules and finally to some location. So what are the changes you see at this location if you are standing, and at this location, and they are coming through this molecular mechanism, diffusion process, those are represented by this gradient of gradient. Okay. And those are happening because of viscous effects, so that is called as viscous diffusion. Okay. So another interpretation of this local thing is, say you have a piston cylinder mechanism. Now you have a piston cylinder mechanism, and you want to record the velocities at this point with respect to the motion of this. So what changes you will observe at one? Okay, since this piston is moving, the velocities of the gases, they are also being changed. Now here some velocity, then so you will see that the velocities with time, they are changing with time. Okay, so this is something you can represent as del u del t, change of u with respect to change of time. So local, you can say this is a local acceleration of those molecules or whatever, this thing. Local, this is local phenomena. is like local acceleration. And what you see here, this bulk acceleration, convective, this acceleration, these are all acceleration terms. These are all force terms. Okay. So this, to interpret that, consider a convergent diverging kind of section. Say you are in a this part, and then you want to move to this part to this part. Okay, 1, 2, 3. Okay. So you have a pressure here, and pressure gradient is existing, so that you have a flow. Okay, so that you have a higher pressure, low pressure, then you move, the flow is moving from left to right. Okay. In that case, if you see what changes are happening, initially at point number 1 there will be a certain velocity, and at point number 2 the velocity will increase because it is a diverging section. Okay, and then you will see that 2 to 3 it may remain constant. Okay, and then in other section, say 4 for example, it is a diverging section, so velocity will fall down and it will drop. Okay, so you see 1.1, 0.2, 0.4, the incidence is happening at this location x. So you see the velocity changing with respect to space. So this represents and the this represents the acceleration, then constant acceleration, and then deceleration. So what are these things you are seeing here? These changes you are seeing, those are nothing but because of these terms. These are not local terms, local things. These are bulk things happening. Okay. And diffusion mechanism, as we said, the diffusion mechanism will not have the component momentum transfer with respect to the bulk motion. It will be through the molecular diffusion. Okay. Now we'll move our objective to derive the conservation of energy. Okay. Why we are now dealing with the course on computational heat transfer, but why you are doing the derivation for conservation of mass, conservation of momentum? Any guesses? Anybody can tell me? Sujoy? Shinjoy?
Yes, sir. Yes, I'm only.
Yeah. See, now we are talking about energy equation, but why you have taken this conservation of mass and momentum also? We should have directly taken conservation of energy, na? Any guesses?
Sir,
Yeah.
since it is a flow processor, the mass does not, rate of mass is changing, no, sir. That's why we are taking conservation of mass and momentum.
Huh. Okay. So I'll make it clear. So he's correct. Okay. So say for example, the energy equation will look like this. So rho Cp. So rho Cp can go. It will look like this. Energy equation will look like this. Alpha is K by rho Cp. So here you see you have U, V, W. Okay. So the motion, this is a convection heat transfer. Okay. This is convection heat transfer. This is local, whatever you see the change in temperature. But this is a convection. This is either forced convection. Okay. This is basically a forced convection. Natural convection is there, then you will have to add somewhere here natural convection part. And this is, we call it conduction. So in conduction part, there is no movement of the fluid. Okay. If it is even in a cylinder, and then you do not consider this movement of, if there is a gas, but it is, you are not considering the convection, only conduction means you do not have to consider the UVW. And since you do not have to consider UVW in fully conduction case, you do not have to solve for UVW. In those cases, for specially conduction case, for conduction problem only, purely conduction, for purely conduction, we do not, U is equals to 0, V is equals to 0, and W is equals to 0. Okay. So you do not need momentum equation. Need not to consider momentum equation. But in general case, when you have a convection also, you need this. So as Viknesh said, we have to consider conservation of mass as well as conservation of momentum. Now we want to derive. So again, we have to consider control volume with control surface, and we have this velocity with which this control volume may be moving, and control surfaces will have to be identified by the normal, and you have the interactions of work and interaction of heat, okay, Q and W with the system. So we can write generation rate of total energy, generation rate of total energy. Let me write conservation of a title energy. Generation rate of total energy in the system can be given as d phi by dt which is nothing but equals to okay, let me represent this by small q, because I'll be then consistent. Q is something which is energy released locally, local energy released. Okay, I'll just write. Let me write here Q dot N ds plus whatever this U sigma dot N ds. Okay, so here this Q is energy released locally, there can be a release of Q locally here, maybe because of some nuclear, some sort of source of energy, heating source, or some heating coil or something like. Energy released locally per unit volume per unit time. And this Q dot N, and it is negative, it is called as heat lost. Heat lost either by conduction or radiation, and this is last term is called as mechanical work done. Mechanical work done mechanical work done on control surface by the stress field. Okay. So there will be a stress field acting, and then you have to consider those stresses on the surfaces. Those will act as a work. So this is nothing but your first law of thermodynamics, and you can write this in a convenient form equals to. Convenient form is you can convert this control surface expression in terms of control volume expressions, and you can write it like Q minus del dot Q plus del dot U dot sigma dV. dV means volume. Now we want to we know that from RTT, from Reynolds transport theorem, we need to we have to find d phi by dt. Okay, so identifying phi, so we know that phi is a specific total energy. We know that specific total energy phi can be equals to E is equals to H. H is a specific enthalpy, and then U square by 2 plus Gz. Okay. So first term is a specific enthalpy. Specific enthalpy, and this is a kinetic energy, and this is a potential energy. Okay. So we can write this d phi dt. If identifying this phi is equals to E, we can write from this d phi by dt is nothing but equals to integral control volume del of del t rho phi. So phi is our E, rho E dV plus integral Cs rho phi. Phi is again our E uds. u dot ds. Now, since n is not there, s become vector. So ds is nothing but here ds is nothing but equals to nds. Okay. So this thing we can write again in terms of control volume del t rho e plus del okay del dot rho eu and can be written as. Now you equate these things. So after equating, you can write integral cv del rho e del t plus del dot rho eu dv is equals to q minus del dot q plus del dot u dot sigma dv. Again, that this expression is for any type of control volume. So for a very small or it's so we can essentially neglect these integrals in the limit, and then finally we can get an expression del rho e del t plus del dot rho eu is equals to q minus del dot q plus del dot u dot sigma. Okay, dv gone, so we get this expression. But still we have some terms which has to be put in terms of e. Sigma is one term and q is also one term, which need to be converted into e form. Then only it will be a convenient form. Okay. Also, in most of the cases, e is not considered, and that e is not considered, and it is expressed in terms of h and h. Okay, it is expressed in terms of h. This also is expressed in terms of h. We need q also, e, this. So e already know that definition of e is defined as h plus u square by 2 plus gz. So substituting this, we can find a suitable expression. Before that, some arrangement is needed. Okay, some arrangement is needed. By that arrangement, we can write d of e total. Suppose e total is there. D of e total is equals to dt is equals to, it can be written like d of e d of h, not e, d of h dt plus u d of u dt and minus g dot u. G is also vector and u is also vector dot u. So in terms of and one this thing, and another is another is like another is an identity, which is del u, and tensor product of del u with sigma is nothing but equals to del dot u dot sigma minus u dot del sigma. So you see the del dot u sigma, del dot u dot sigma is already here, and what do you need is u dot del sigma. Okay, so u dot del sigma is coming through something else. So from the momentum equation, we know that momentum equation is d du dt, u du dt, rho du dt. Okay, so that has to be obtained from the momentum equation. This thing. So from momentum equation, okay, and u dotted, take u dot of momentum equation, which will give you rho u dot du dt is equals to u dot g plus u dot del dot. Okay. So here we have this expression. Then from this you can get u dot del dot u is nothing but rho u du dt minus u. And knowing these things, these things will get cancelled out once you substitute d total there. Then finally what you get is, so substituting this 1, 2 and 3 here, this E can be this is nothing but E dE by dt. So H is substituted here, U is also substituted. So for the E, this definition is substituted here, and you write that, then you will get these expressions. So these expressions finally will get cancelled out, because we have the term like this. Okay. So that you can understand from this. If I write a final equation which is representing like this. So our final expression is like rho del h del t del h del t plus u dot del H, Q dot del H is equals to Q minus del dot Q plus del U vector product of sigma. So since sigma is a tensor, you can represent by 3. Right? So these things you could write like this with having that another term and this term, and you could delete these terms from the definition of total energy. Okay, or you say E total means here you can write in terms of that, let it be E total only, del E del T. Okay. So that we can get terms like this. Now, if you have this Q is equals to 0, okay, we can get an expression like this. So if Q is equals to 0, if Q is equals to 0 means there are no generation or any source of heat generation, Q is equals to 0, and if there is no convection, U is equals to 0, and we have anisotropic and isotropic inhomogeneous. Written in CPT form. CPT, rho is already there. So we can write this as this also can be written for a simplified special cases when H is a function of T and pressure, T and P, when H is a function of T temperature and pressure. Pressure dependence is very small. So generally Cp is defined as del H del T at constant pressure P, and by definition defining this you can write this expression as rho Cp del T plus U dot del T is equals to, and noting that Q is coming from the Q is coming from this Fourier's law. Fourier's law. These are called as subsidiary equations, constitutive relationships. Constitutive relationship. Relationships. These are needed. These are coming from experiments. Experiments conducted. So Q is nothing but this Q is nothing but equals to K gradient of temperature, okay, or grad KT, grad T. Okay, so you can write del K grad T instead of that, and Q, and understanding that this is a viscous dissipation, and viscous dissipation, assuming that viscous dissipation is very small. So viscous dissipation or negligible viscous dissipation, it is this expression. So for this case, for example, if Q is equals to 0, U is equals to anisotropic and inhomogeneous. What does it mean anisotropic and inhomogeneous? So if you have this Q and U is equals to 0, then you have rho Cp del T is equals to del dot K grad T. This much only you have. This is your well-known conduction type of equations. Okay. There is no source of heat, there is no convection, only conduction and temporal changes. Okay. Now here this del dot K gradient of T. Now K is either a constant or it can be a function of temperature also, or it can be varying from the space to space. Okay. If it is varying from space to space, if this K is a function of space, then you cannot take it outside. If that is the case, then you have for this anisotropic inhomogeneous material and 2D, for example, in that case you have to write this expression as rho Cp del T is equals to del dot. So del dot I am representing now del x K 1 del T del x plus del x K 2 del T del x del y K 1 del T del y plus del y K 2 del T del y. You got this? So K is nothing but it is a K11 matrix, K12, K21, K22. So you do not have the K a single value. So you have to write this expression. If it is K is the material is isotropic and homogeneous and 2D, then isotropic, homogeneous and 2D, then rho Cp del T del x will become K become constant. So del x K becomes constant. So that only one K will be there, and this K12 and K21 will be zero term. So you have del square T del x plus K del square T del y square. Okay. K is a constant now, so K can be taken out and you can have del square T del x square plus del square T del y square. This is time. So physical significance again is similar. This first term you see, this is whatever is happening inside this. So if you are standing here, you would see the locally change in temperature. If there is any change in temperature with time, at this moment you are feeling some temperature T, and in another time you are getting some another value of temperature, hot, cold, like that. So whatever these changes happening with time in that particular location, fixed location, that those changes are local changes. Okay. So locally you are feeling those changes. Now suppose you move from this space to this space. So while moving with this velocity u, you also see some changes in temperature. So here you felt it is T1, you felt it is T2. Okay. So this, and there is a gradient. T2 may be higher than T1 or T2 may be lower than T1. So there is a gradient. So in the gradient, in this, if you are moving in the direction of gradient, okay, or gradient of this moving with this u, you see a change. So that is nothing but a convection you see, you feel. Suppose you move in a y direction with velocity v, then you will feel some other temperature here. Okay, so that is nothing but whatever you see a spatial. And this third thing you are saying, this is a diffusion term. This diffusion is irrespective of movement of view. Suppose you are here at, suppose you are here and here, both without moving yourself, then you see a change. Okay, not like this. Here you moved from this, and then you felt a change with, while moving with this velocity. Now assume that you are not moving with any velocity or something like that, but you are present somehow at two locations. So whatever you see, whatever you feel, without bulk motion, without effect of bulk motion, you don't feel any bulk motion here. Here you are feeling the bulk motion. While moving through this space itself, you felt some temperature changes here, and then finally T2. Here you are not doing. Here you are just simply at this location and at this location, and you feel that here there is a TA and here there is a TB. And whatever this TB you are seeing, it is coming from this TA only. If it is a hot, then it will transfer heat to corresponding molecules, and then finally it will reach to the B location wherever. It is transferring not to A and B only, it is everywhere. Everywhere these molecules are transferring to nearby molecules. They are keep on transferring this energy to nearby one. And that process is called as diffusion. That is happening all molecular level. And whatever you see in the second part, u dot del T, then that is due to u dot del T, that is due to the bulk motion. So bulk motion of, here you have a motion of fluid, bulk motion of the fluid. The particles here, they are moving here. So, okay, so with this, we have completed the derivation parts of conservation of mass, momentum, and energy. These equations we will continuously use in our, CFD. So, okay, so I'm stopping the class here.